So before we can talk about chemistry in the stratosphere, we got to go make and break down stratospheric ozone. Before we can do that, we got to talk really quickly about ultraviolet, UV, which is part of the electromagnetic spectrum. We say that it's higher energy than visible life. That's why it's ultra. It's like after visible light. That's why it's after purple. It's like very purple, ultraviolet. So you've got the Roy G. Biv, and then if the energy has more energy, then it becomes ultraviolet. You should know that high energy comes from shorter wavelengths, and you should know that lambda is the physics variable for wavelength. Remember that a long wavelength is lazy, but a short wavelength takes a lot of work. So just kind of cruising. Takes more energy to do that over a shorter area. There's 3 types of ultraviolet, and I'm sorry you do need to know all this, but you do need to know this. They're UVA, UVB, and UVC. UVC has very high energy, UVB has less energy, UVA has the least energy. And so UVC has an extremely short wavelength. You can see that on the screen. And UVB has a medium wavelength. And UVA has a lazy wavelength. UVC is such high energy that that's going to break up any bond. If you have any chemical and UVC comes by, it'll break something off. Energy is transferred. One of these atoms becomes independent. UVC stops being UVC. It gives away its energy to that bond, and that overwhelms the attraction, and you break up compounds. Best way to know this, if you don't understand what I just said, it would be good enough on the AP test. You can just say breaks bonds. It destabilizes compounds. It breaks up bonds. UVC can break up almost anything. This is not exactly accurate, but if you were exposed to like pure unfiltered UVC, like outside our atmosphere, if you were like in a spaceship with a plain window and you had UVC unfiltered and unblocked hitting your body, you'd start to feel a little bit warm, and all the dead skin, you know, the outer layers of our skin, all your dead skin would start to just powder off. You would see like dust. And all of a sudden you'd start to feel a little warm, and you'd be kind of like pink, you know, like raw skin. And then it would start to like burn, and it would start to sizzle. And literally it would be like burning, like the experience would be of burning. And if you waited long enough, you'd fizzle. It would take a while, but it's like slow motion Alka-Seltzer. UVC is very dangerous. It breaks all bonds, pretty much all bonds. So thank God the upper atmosphere blocks it all. There's so much energy that as soon as a single molecule of anything meets UVC in the atmosphere, UVC breaks up. So I'm going to skip slides real quick. You can see that UVC is blocked in the atmosphere. UVB is like a medium energy, still does a lot of damage. It's still dangerous to life on Earth. And that UVB wavelength is like a perfect match for this one magical molecule, ozone. Like, thank the gods. This is so lucky that ozone, O3, is the exact size of bonds. The distance is perfect to block UVB. Ozone layer blocks 99%. A teeny bit of UVB hits the Earth, a very small amount, but most UVB is absorbed by ozone. That should have said 99%. It's almost all of it. And UVA has the longest wavelength, so most bonds won't line up right, and UVA can just sneak through. A good visual that I've often seen to explain blocking and ultraviolet, if you'll forgive me really quickly, if you've ever played what's it called? Pinball? I'm blanking on the word right now. I think it's called pinball, right? Pinball machines, where you like have a big metal stainless steel ball that like is on an angled platform and there's bouncers, and you use those little tabs to like hit the ball around. Pinball machines. If you're playing pinball, every now and then you'll see like those three bumpers together, and the ball will just move through them and nothing happens. But if you get it right, that ball will go ding 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 ding, and it just kind of like spills out. That's a great way to think about how ultraviolet interacts with chemical compounds. If you imagine a pinball coming through bumpers and it's curving like this, when it gets to a bumper, it's going to go and give up all of its energy, right? And if you imagine a pinball moving like this, the chances are pretty good that it's going to get stuck on one of those three things. But if it's just snaking really slowly, it might slip between those bumpers. That might be a stretch. I'll show you a slide. The wavelengths are really different. So they really affect the likelihood of that energy interacting with a chemical compound. Imagine that like triple bumper thing with another triple bumper thing and another triple bumper thing. If the wavelength is really long and lazy, it might just tuck through all those. That's ultraviolet A. If the wavelength perfectly matches that spacing, well, all it has to do is hit one of them, and then it goes bing, 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 and it gives up all of its energy. And if the wavelength is super short, it's guaranteed, because all it has to do is just run into any bumper, and that's going to give up its energy. You have to know that. So ultraviolet C is blocked by everything in the atmosphere, because ultraviolet C gives up its energy to any bond. So it's completely blocked by everything in the atmosphere. It breaks all bonds. You have to know that. UVB is almost perfectly matched for ozone. So about 99% of ultraviolet B is blocked by our ozone layer. You have to know that. And ultraviolet A has such a long wavelength that it can get really, really far without interacting with a single chemical bond. Ultraviolet A can penetrate your skin, even though you have this really fancy high technology skin, which has all these layers of dead stuff to increase the density of chemical compounds so you get better blockage. You know, your outer layers are just a whole bunch of like desiccated stuff, no water in the way, just a whole bunch of dead skin cells to hopefully block out ultraviolet A, because ultraviolet A can get way deep into there. Ultraviolet A gets way down into the ocean. Like all that water molecules, it's still scooting through it. Ultraviolet A has the lowest energy, so its damage is limited, but it makes it really far. Okay, so ozone blocks any ultraviolet C that's left at the ozone layer. It blocks 99% of the ultraviolet B and doesn't really affect ultraviolet A. I need you to know one last thing. Extremely dangerous. Skin cancer, cataracts, sunburn. This is the one that the ozone layer normally would block. And ultraviolet A, premature aging, wrinkling of the skin, implications in skin cancer, but most of that is from ultraviolet B. That's why the hole in the ozone layer raised cancer rates, because more ultraviolet B got through. You can ignore this schematic about blocked and this one making it through. That's probably confusing. So you have to know extremely dangerous, blocked by, that should say the whole atmosphere. You have to know these, and that should say 99% blocked. And you have to know these, that should say basically it all goes through the ozone layer. So this is a good explanation of the types of radiation, but a bad explanation of the ozone layer. All right. That may be confusing. Write down a question, come ask me.